Well, welcome everybody. I have a slide for that. Thank you. Cool. Welcome. Who's interested in space?
Woo! Yeah.
I said, who's interested in space?
Woo!
Yeah, exactly. Okay, that's what we like. Cool. Well, first of all, before we get started, I want to say thank you very much to Entrepreneur First. You'll see this logo around on the walls for hosting us. So, a huge round of applause. Thank you for Entrepreneur First for hosting us. Entrepreneur First is an awesome organisation, awesome people. So, can you guys wave at the back? Talk to James and Trey and Kitty. Talk to James, Trey, and Kitty, and Jack. Okay, there are loads of them. That's great. Go talk to the Entrepreneur First people later. Just hear what they do and what they've got to say. It's awesome. So thank you very much for hosting us. Yeah. Okay, so one of the first questions for those of you, actually, who's been here before? Who's been to one of the Future London events before? Okay, so about half the room. This is good. So for those that haven't been to one of these before, you might be wondering, who's here? Who are these people? Okay, so I've got a little bit of a rant maybe, that if you want the written down, well thought out version, you can go to futurelondon.org and find out. It's at the bottom. You're probably looking around yourselves at the world and despairing. Technological progress has stalled. The world's at war. People are finding every way they can to believe things that are very clearly not true. There's something weird going on. The bad news is you're not imagining it. It's actually happening. Everybody else in this room is looking around and thinking this is crazy. The good news is that that's giving you an opportunity to be the hero that saves the world. You get to be Tom Cruise. It's pretty cool. So there isn't any more time to look around at the world, look at the status quo, and expect somebody else to fix it. Those people that were going to fix it have retired, gone golfing, or died, honestly. They're not going to fix the world for us. It's our time. They failed to make civilization better, and worse than that, they failed to prepare us to make civilization better. Those of us in this room. So, you lot, me, all of us, we're the last chance to fix this. Our generation, whoever it is in this room, all of us and our peers, we're the last chance to fix this, to make the world better. And so, we've got to look around and think, who are the people that are going to be doing this? Who are the people that are going to be making the world better? It's not going to be the people that are stopping us from building nuclear power plants. It's not going to be the people trying to stop us from building houses. And it's definitely not the people striking at the thought of automating trains. So who is going to fix the world? Who's going to take us forwards into the building colonies on Mars and personalised medicine and flying cars, if you were here at our first event? So we're the ones that have to make it happen. And we have a choice. Are we going to build the tech that's going to fuel the next 500 years of innovation and wonder? Or are we going to live off the nice wine and decaying infrastructure of our grandparents? Yeah, nice wine's good. I agree. So the question is, can we do both, right? Nice wine and invent the future. It's good. So, in answer to this question, who are we? We are the people that are going to build the future. We are not the orphans of the past. We're the children of the future. And so, yeah, woo! That's it. Exactly. So, we're builders. We build things. We're building the future. We're inventing the things that are going to be fueling the next 500 years of innovation. We're ambitious. We think the future can be better. Not just might be better. We think it can be better, and we're taking that on ourselves to do. We're optimistic. Not only can it be better, it will be better. It will be better than it is. And it's already pretty good, right? It's been getting better over time, thanks to capitalism. Good. Woo! Capitalism. And we're also a community. So half the people in the room, raise your hands again if you've been here before. About half the people have been here before. This isn't just a one-off thing. This is a continuation of people. And so the community is called Future London. And right now, it's not the best name, because it implies London, but it's actually a bunch of people. We've got Jugal here from San Francisco, phoned all the way just for this event. That's not true. we're talking about the future, right? We're in London, but we're talking about the future. So this community, it's not just this room. It's not just people that are talking about space. It's talking about all the other events we've been running and the events we will run. It's about everything that you in this room might do, and the other people that might be in this room might do. And so, our sort of theory of change here is step one, build this community of people that are interested, optimistic, ambitious for the future. Step two, we expose you to ideas that you might not have been exposed to before. And so that 50% of people, they either came to an event about cars, flying cars, that is, or an event about building houses. Kind of random. Why are they at a space event? That's because we're exposing people to ideas that are different to the ones they experience in their normal day-to-day life. And then step three is calls to action. So we're still working on this. We'll come to this in a moment. Once we've got this cross-discipline community of people that care about the future, they're ambitious and they're optimistic, we then say, these are the things that are going to be most effective for improving the future. San Francisco is fantastic for I think, really one particular reason that London doesn't have. London has all the talent that San Francisco has. What San Francisco has is Americans, right? They're really good at self-organizing. But in London, we're a bit shy, and I'm trying to remove my shyness and be the person that suffers the awkwardness. Trying to be the person that suffers the awkwardness of trying to pull people together and stand in front of everybody with a microphone. But all of you can do that as well. So we're trying to gather people together to go and solve these problems together in this cross-discipline community way. And that's something that San Francisco is really good at. So, calls to action, we're working on this at the finale. Sign up for the finale, it's on the website. We're going to be announcing our cause areas and a couple of the specific ways you can get involved in actually building that future where we have Dyson spheres and flying cars and people from the UK living on the moon. Cool. United Kingdom of Northern Ireland, Great Britain and the moon. So, calls to action are coming. It's going to be cool. We have a WhatsApp group. This is part of the community piece. We have a WhatsApp group. Scan that QR code for this event. So if you're interested in space, you're interested about the future, you're ambitious, you're optimistic, join that WhatsApp group, talk about space stuff, talk about ambitious, optimistic stuff. It's part of a WhatsApp community. You may or may not be familiar with those, but there are a bunch of other groups that are part of that, including AI and house building and future flying cars and things. So if you scan that QR code, you'll get into that. Wait for people's phones to go down. Don't put them away yet, because we've got another QR code. I love me some QR codes. Future House. So, this is the first time we're mentioning this publicly, but it is something we've been talking about. London is awesome for private members organisations. We're creating a private members organisation for builders, ambitious, techno-optimistic builders. And so we're at the beginning stages, actually this morning and tomorrow morning, we've been looking around a load of different spaces, and tomorrow we're designing a space, which is really exciting. We're going to walk around and say, walls there please, no walls there please. And it's going to be a members club where you can come, drink beers, co-work, use 3D printers and CNC machines, do FPV drone racing, figure out how to build a model Mars rover, all this stuff in one building with all the other people in this room, where everybody's there as a peer, as an equal, saying, how do we build a better future? How do we build this sort of ambitious, optimistic vision that we all have? So we're going to be sending a bunch of sort of polls and questionnaires and things in here. So we'd love to have you join the group so that we can send things your way. We'll keep you updated and ask lots from you. But at the moment, it's just getting your opinions on what you want there. So you're all here for Space Things. Thank you very much for indulging me. We've got Anatoly from New Orbit. Where are you? Fantastic. Okay, so you're going to hear about from a few speakers. We've got 3 speakers, and then we've got food that just arrived. So, Anatoly, hand it over to you.
Yeah, thank you. Woo! So yeah, it's great to see everyone. It's great that the community is growing. Thank you very much for very inspiring speech. I think while we talked about, and the topic today is about going to the moon, I want to talk during the next 10 minutes about how we actually can come closer to the Earth and why it's important. If you are familiar with aerospace industry, you usually have two things, planes and satellites. Usually you have planes that are flying at 10 kilometers and you can see them from the ground, but you also can see Starlink, Planet, and all of the other space companies operating at usual low Earth orbit, which is 600 kilometers. But the interesting thing is that today's satellites, they are not built to operate at much lower altitudes, so-called ultra-low Earth orbits. So today there are no satellites that can fly effectively below 500 to 600 kilometers, and this is a big problem because the technology doesn't exist, but it provides incredible benefits. The first benefit is that imagine if you put the same camera to 600 kilometers and 200 kilometers, this is the difference in resolution that you will receive from the same satellite. And you can see that this is, poor image, coarse, you don't see anything there, but here you can see incredible things. You can see numbers, you can see signs, and basically these orbits can provide you with the most precise and the most detailed vision of the world, providing you a lot of different insights in terms of, weather predictions, cataclysms, and many other things. And it also appears that if you go lower, everything becomes better. So if you want to do different types of radar imagery, you can make about 20 times more images for the same satellite. I'm not sure if you recently heard, but Starlink right now can connect directly to your iPhone. And the interesting thing is that right now they only can support voice calls and messages because it's very small bandwidth. So in our case, if you reduce the altitude in 3-4 times, your bandwidth increasing by 10 times. So it means that you can do video calls, you can do web browsing, or you can serve about 10 times more people, which is also incredible. But it also solves one of the biggest threats in the space industry, which is space debris. So this is, if you can see, this is the altitudes of conventional satellites, and this is most of the Starlink satellites. You have about 7,000 satellites which are right now at these orbits, and if two of them collide, they create trillions of small space debris that stay there for 10 to 20 years. And this is how the orbit looks at ultra-low orbit. There is nothing. There is only 60 objects at these orbits, and if two satellites even collide at these orbits, they will deorbit within just 1 month. It means that if you think about this, if you can build a satellite that can fly at these orbits, it has much better performance, order of magnitude better imagery, better telecommunication services for the whole world, and it also doesn't pollute anything. You can save our planet. But there is a big problem. The reason why there are no satellites there is because of very high aerodynamic drag. So if you put any existing satellites today at these orbits, you would only have about 1 month of lifetime before the satellite deorbits and goes into, just evaporates in the atmosphere. And this is a big problem because if you want to stay at these orbits, you need to make sure that you can operate for more than 5 years to make it economically viable. And one of the ways how you can stay there is that you can counteract the drag at these orbits and stay at these orbits for a very long time. But the problem is that you need to store about 50 to 100 times more propellant to stay at this orbit. This makes satellites large, unusable. You cannot really build them, you cannot launch them, and this is why satellites cannot fly there. But we in New Orbit found a very interesting solution to that problem. We actually built the first satellites that will be capable to operate at these orbits because it uses a very specific propulsion system that you can actually see here. So how our satellite works is that instead of storing this huge amount of propellant required to stay at the orbit, we take everything right from the atmosphere. We collect the gas of nitrogen and oxygen. After that, we put it at the thruster at the back. We use solar power to accelerate these particles up to 100 kilometers per second, and that allows you to stay at these orbits. And you can see this thruster here. So this is I'll show you later, and you can come if you are very interested. And the interesting thing is that it seems like science fiction. And did people really think about this before? The interesting thing is that they did. A lot of people really tried to build these engines, but we in Uorbit became the world's first to show that you can fully compensate for drag at these orbits and really stay at these altitudes, which means that you can really unlock these orbits. For the first time in history, you can get much better performance. You can remove all of the space debris. And this is the engine that you can see here. So this is the engine that is working in our vacuum chamber that creates the environment of space. And this is how it looks like in reality. So this is the plume of the air. So we basically, what we do is that we take the air, we put it into this thruster, which is just, the air is just a gas. We create the plasma by applying different electromagnetic fields, and after that we accelerate them up to 100 kilometers per second. Can you imagine? It's very, very high velocities. And in that sense, particles hit you with 8 kilometers per second. You throw them with 100 kilometers per second, and that allows you to stay at the orbit. And if you think about this, we think that the future is this type of ultra-low Earth orbit satellites, because it has 10 times better performance, it doesn't leave any space debris, it has, you also operate under Van Allen radiation belt, and you operate under 20 to 40 times less radiation that allows you to use GPUs instead of CPUs to produce much better imagery or post-processing and many other incredible things. And why we are also very hopeful about the industry is because if you look at the number of satellites launched every year, by 2019 there was 100 satellites per year launched, and after that there is 2,000. And it's expected that with the Starship it's going to be more than 100,000 satellites launched over the next decade. And if you think about this, there are no better satellites than the satellites that can operate at ultra-low Earth orbit. And right now we are the only company that have this technology. And we as a company, we want to provide access to everyone at these orbits. And in 5 years, we have a goal to make in Britain the world's center of the satellite manufacture. Because, if you compare our satellites to usual satellites, it's like comparing cars to horses. Horses leave manure, satellites leave space debris, ours doesn't, and ours is much faster than usual horses. But before we go there, it's also for us right now is one of the most important stages of the company where we are building our first space mission. So we will launch our first space mission next year. We call it Mission Phoenix. And we recently raised a 7.5 million Series A from the Silicon Valley investors, CSVC. We have participation from Lifeline Ventures, ATL, and also the ex-chief science officer of NVIDIA also invested in us. But what this mission will entail is that we want to show that our propulsion system that can unlock these orbits really work. And we basically can unlock these orbits for the first time in history. So I think it's great to look after us. So, and if you have any questions, please let me know.
Thank you very much. We're over food and drinks. Make sure you come and grab Anatoly and have a look at the ionic thruster and ask the questions. I think it's an ionic thruster, right?
Yes.
Yeah, cool. Awesome. While Emily comes up, yes. Do you use, I'm just curious, do you use the solar panels for lift as well? Do you frame them as wings? Because they kind of look like wings.
They're only 20 drag.
They only drag, okay, great. We've got a HDMI or USB-C, which would you prefer? It's funny, the different events with the different sort of industries for speakers have different laptops. This is a very Windows-heavy speaker panel. The HDMI cable is somewhere on the floor, I think.
Hi, I'm Emily. I've taken a slightly different tack to Anatoly because when the question was posed by Joe about why hasn't the UK got to the moon yet, the Peregrine mission was about to launch and we were days away from having UK science technology on the moon, and so I objected and said, well, we're nearly almost there. And then we weren't. Because space is hard, and that's okay. But we're here and we're very almost at the moon, and actually in places we've gone beyond the moon, so we'll talk about that in a minute. But I come from a different background. I'm not an engineer, I'm not a scientist. I spent 7 years working at the UK Space Agency, where I was one of the delegates to the European Space Agency and spent a whole load of your lovely taxpayers' money on an awful lot of cool tech, some of which we'll talk about today. And I spent an awful lot of time just exploring what space can do and the art of the possible. So I thought I'd talk a bit about that today, as well as what a couple of my companies are doing as well. So we're already getting there, and we've gone a little bit beyond already. And John will love this picture, because he's going to tell you all about ExoMars later. But this is our lovely little Peregrine mission down here that had some UK scientific bits on it that were due to get to the moon in a couple of weeks' time and didn't quite make it and won't quite make it. And that's to do with the propulsion system that seems to have gone a bit wrong there. But that's unfortunate. But we've gone so far beyond the moon already as a UK entity and what our endeavours are. We've got the JUICE mission, which is on its way, launched last year to the Jupiter's icy moons, and we're leading some of the scientific missions out to there. We've got missions here, the biomass mission, which Airbus are working on. I presume John knows about that one as well, which was due to launch last year and will go this year instead, probably. And that's going to look at all the biomass around the world. What are we doing around carbon capture? What are we doing all around the world on forest burning, and what impact is that having on all of our environments? We've got MIRI down here, which is on the James Webb Space Telescope, so all those beautiful images you can't see coming back to Earth. Actually, a whole load of UK scientists were really involved in building that. And then we've got Quantum. And I've put did it deserve an oon? Not yet. Not yet.
I'll wait.
Quantum's cool. If you don't know about the Quantum satellite, it's one of my favourites, although someone in this room did tell me that they clearly had a different experience of working on Quantum than what I did, because I worked on it as the ESA delegate. Quantum is cool because 15 years ago we had no idea what we'd currently be using space tech for. And Quantum is the first reconfigurable satellite that we've put up to space, and it went up a couple of years ago. And the whole time it's up there, you can reconfigure what you want that satellite to do. You can change the mission, and it's the first satellite that's going to enable you to do that. And that's leading on to a whole family of other satellites built here in the UK. Well, actually, that for me is how space becomes sustainable. Because we don't know today what we're going to be needing space for in the future. We know that we're going to be needing space for a whole lot of stuff across Earth, and we'll talk in a minute about a few things that probably you don't think space is used for, and it really is. But actually, Quantum for me is where space sustainability really gets cool. As is the Rosetta mission and bedbugs. And I promise they're linked. It's just you don't know how yet, but you will in a couple of minutes' time. The Rosetta mission went up to find a comet, find the comet that's about 510 million kilometres away, and we launched on it to do science. Great. Science is cool. Science is fabulous. But actually, what science brings back to Earth for me is even cooler. Because one of the things that Rosetta did was have the Philae lander on it. And the Philae lander was all about looking at what gases were coming out of the comet. And the guy who worked on that gas analysis, that scratch and sniff stuff, was based at the Harwell campus in Oxfordshire, which is where I was based for a while. And he walked, we offered the chance at Harwell a number of years ago now to say, have you got any problems and can space help? And this chap walked in a suit, and from his internal pocket he pulled out a test tube and it contained bedbugs. And he said, this is my problem, can you help? I'm like, what the heck, why are you bringing bedbugs to a space event? But the answer was yes. Because the scientists in the space domain are never short of ideas. And it turns out that bedbugs leave a smell and a scent trail behind them, which is very similar to the scents that were being explored on the comet as part of the Philae lander, as part of the Rosetta mission. So the scientists based at Harwell used that same scratch and sniff technology to find where bedbugs are in hotel rooms, on buses, and wherever else around the world. And there's now a handheld device using science from the Rosetta mission here on Earth finding bedbugs, which is pretty cool, I think. And that same tech is now being used on breath tests as well to discover stomach cancers and things like that. But for me, this is space sustainability in action. Because you go out, you do the cool science, you go out, you find out more about our universe and our Earth, and you find out a way to find the bedbugs and get rid of them too. Woo! Thanks, Joe. Likewise, jellyfish. Now, I quite like power. I quite like knowing that I can turn my cup of tea on, and I don't like it when my power goes off and I can't get my cup of tea, and I don't like it when my power goes down and my internet goes down. But we're moving towards nuclear power around the Earth. And nuclear power has to be by water, so you can cool the systems. We all know that. That's fine. Big problem for nuclear power, jellyfish. Because when you get jellyfish into your nuclear reactors, that causes a huge amount of problems. You have to shut your nuclear power station down for weeks, and we run out of power in this country. What's space got to do with all of this, eh? Right. Jellyfish can't see them from space. You can see the trail they leave on the top of the ocean surface as they move as a great mass of jellyfish. And you can give that warning to the nuclear power stations and say, shut down early. Stop now, don't let those jellyfish into your system, and that means I can still have my cup of tea, we can all have our internet. But there's more. Because it's not just about finding the jellyfish and telling the nuclear power stations to shut down. Who wants jellyfish? Jellyfish are the only animal in the world that are not banned by any religious text. Cool fact for you tonight. Why is that important? Jellyfish are made of collagen. What's collagen required for? Makeup. Therefore, makeup people all around the world who manufacture makeup want the jellyfish so they can get the collagen, so they can make makeup and sell it to people all around the world. We are using that same data that we're selling to the nuclear power plants to say, avoid the jellyfish, to sell that data to the makeup industry to say, go find your jellyfish, and to the fishermen, sustainability in action, using the same data, the same information, all based on using Earth observation done by UK satellites, etc., etc., all good. Same data, really good thing passing all around. But what's next? Well, one of the companies I do work for, because I probably should mention what we do sometimes, is working on in-situ resource utilisation. Now, in-situ resource utilisation is where you go to the moon or you go to somewhere else and you take the minerals, you take the things out of the moon or the comet that you've landed on, and you use them while you're there. So what we're working on here is this device here. It will launch in a couple of years' time. ESA website says 2025. Don't believe everything you read. And what we're doing there is we've developed a scoop, a grabber, to pick the lunar rock up. We're going to crush it, run it through a catalyst, and produce oxygen in situ on the moon. That's 5 years' work, summarised in about a sentence, and I've probably done a great disservice to my engineers, but you know, that's so be it. That's what we're doing here tonight. So what that means is we can then develop oxygen, other minerals, hydrogen, etc. in space that can be used for astronauts to breathe, that can be used for growing stuff, it can be used to power things, because that's when it gets really exciting. Because if you can power stuff in space, if you can take that oxygen and hydrogen and use that as a power source, suddenly you can get further. The gravity on the moon, we all know, is so much lower than what it is if you're trying to launch from Earth and go direct. So use the moon as a stepping point to get out there. The moon also happens to be roughly the same size as Australia. Well, one of Australia's main exports is mining. Makes them an awful lot of money. Now, we get into a bit of legal ethics and space policy here, which all gets a bit dubious. But actually, the moon is very, very similar to the Earth. Not quite the same, doesn't have an atmosphere, but constituently in terms of elements and rocks and things like that, it's very, very similar. And we know that we're running out of some stuff here on Earth. So is there an opportunity, if you can do the in-situ resource utilisation and you can bring it back down again, is there the opportunity to go up there and actually bring stuff down that we need here on Earth? Yes, there probably is. And by about 2028, there's a Moonlight bit of project going on led by the UK, which is going to put a whole communication of comms network around the moon so that there can be continual communication between science missions, astronauts, rovers that are up there and everything to enable very fast data relay between the moon and the Earth. Towards a lunar base, but it can be used for this as well. But if you can get the oxygen and hydrogen up there and you can use the moon as a jumping point off, then you can use Anatoly satellites in the very low Earth orbit, but you can then use water propulsion and sustainable propulsion to actually propel something when you've got in space. And you take a bit of liquid up there to actually get you to space, or to move you around in space to get you to the moon, but then you can pick up your resources as you go. As you travel through space, you can use that sustainable propellant. And another company that I'm working for the sister company of the one who's doing the in-situ resource utilisation, is working on how do you use that propulsion? How do you take something that's as small as something you can pop on your fingertip there? You use hydrogen and oxygen you've picked up in space, or that you've electrolyzed using water you've taken from Earth, and you can use that to travel through space and do it sustainably, do it in a green way. Water, if you use it as a propellant when you're fueling your spacecraft, costs a heck of a lot less than hydrazine to use, because you don't have any of the health and safety problems. I can go and drink it, and then you can fuel a safe spacecraft with it. It is that simple. You have to deionize it, and I'm told you're not allowed to use the lavender-smelling stuff from Sainsbury's. It's frowned upon. But it's pretty much the same stuff, so it's really, really, really cheap. But you can actually go ahead and do space sustainably. You can take what we're learning from our missions and do it sustainably. You can take what we're building here and do it sustainably. But you can also... We don't know what we can learn from it yet. We know that what we're having to do with oxygen, hydrogen, and water propulsion and space tech is very similar to what you need for hydrogen-based cars. So I'm willing to bet that there's going to be some some technology transfer back again into the hydrogen car industry and to that area as well, because we don't know what we're learning from this space exploration yet, but I sure as heck know that it's interplayable with what we're doing here on Earth. So for me, we haven't quite got to the moon yet, thanks to the mission failing, but we will get there, and the Artemis mission says we'll have UK boots on the ground on the moon very, very soon. But we are doing an awful lot. We're getting an awful long way, and we're doing it sustainably. And for me, the future is really exciting, that we can make space green and take it further into the future. So thank you for having me this evening.
Thank you so much, Emily. I think we can all get excited about making Mars green, right? Yeah? Make space green. I like it. Okay, Peter, you're going to hear about making space green, I think. No. We'll hear about what Peter's got to say for us. Okay, we've got an HDMI or USB-C. Cool. Okay. It's not Windows this time, yeah. We're just keeping tally. So we've got a whiteboard over there somewhere. All you need is mouse. Do you want to? So we've got Peter, and then we've got bao buns for lunch, for dinner after Peter. So I'll take it away. No.
That's still very
We can change the settings, or
that's fine. It's
Great.
fine. Yeah.
Peter.
Hello everyone. This is a bit of a change of topic from the previous two. That was very specific things. Now I'm zooming right out to the big picture of colonising space. Some people like to use the term settling space, but it doesn't matter. It's people pick on words anyway. So my original title was Why Colonising Space is Easier Than You Think, and it is. I added, but it's still hard, because none of it will be easy. But I'm giving this talk because I've noticed there's a lot of popular science, I guess, as well as some actual scientists saying these things, that there's essentially some unstoppable barriers that are going to make this impossible this century, and there aren't, really. So, who am I? I did my PhD in astrophysics at the University of Leicester. While I was there, I did work on a CubeSat project here, and I think that's me.
I'm one of those three people. I'm not him. Yeah, that's me. Unfortunately, this CubeSat never made it to space because the university just wouldn't give enough funds.
But that's much better. I was able to do my PhD in astrophysics on the galaxy rotation problem. I did a postdoc at the University of Cambridge, and I worked on radio astronomy there. And I've also briefly worked in industry. I don't know if anyone knows this company. It was a hardware security module place. I left before they had a big data leak. It wasn't my fault. And now I work as a scientific software engineer in the MRC Laboratory of Molecular Biology in Cambridge, because I'm applying this astronomy imaging stuff to imaging the brains of Drosophila larva. You might have seen that in the news about 4 months ago. That was one of the papers this lab released. But I'm not actually talking about any of those things that I do. So that's my day job. I'm also doing sort of, on my Substack, we can get to through here, I'm doing sort of independent analysis of the state of the space industry and advocacy as well. I'm actually advocating for colonisation. I work in a little space history there as well. And I've done some mission studies and designs as well. So, here a lot, we can't colonise space, it's not going to happen. And there's a few common things that come up. Like, the radiation is going to kill us. As soon as we're outside the Van Allen belts, everyone's dead. Ignoring the fact that like a dozen or so guys have gone outside the Van Allen belts, come back, and most of them have since died at old ages of natural causes. Ignoring that, the radiation will kill us all as soon as we leave Earth orbit. We can't go anywhere until we have 100% closed loop life support. Everything has to be recycled, because if you're on Mars or whatever, you can't get a resupply, so if anything breaks, everyone dies, and it's horrible. And the gravity is too low. Nobody can thrive in 1/6 gravity on the Moon or 40% gravity on Mars. So I'm going to sort of address some of these, and I think I may have made too many slides, so this might be quite quick. So first off, radiation. This is quite commonly misunderstood. So there's two types of radiation that you tend to deal with in space. This is sort of particle radiation, not the sunlight. If somehow your skin got exposed in like open space, aside from the problem you're dying because you don't have a spacesuit, you would get a very nasty sunburn, but that's relatively minor concern. This is high energy protons and other atomic nuclei. There's two components: galactic cosmic rays, GCRs. These are really high energy stuff from outside the solar system, from various astronomical phenomena. They will go through like a meter of material, and they don't give you you can't get radiation poisoning from them, but they give you this constant sort of soak of radiation over time. So it says 500 to 900 millisieverts per annum. The occupational limits in the US is 50, so that goes over it by quite a bit, although it's still at a level where there's not really a lot of evidence of a disease in humans from it. It's an active area of research. The other one is solar protons. So the sun just spits out protons, and occasionally it spits out a very large number of protons. These are a risk for prompt radiation injury, possibly killing you, but they are much lower energy and you can shield them fairly easily. There's also trapped particles in the Van Allen belts around the Earth. You want to avoid going through the inner belts particularly. And finally, there's secondary radiation. So I mentioned, this is specifically a problem with cosmic rays, is that if you have like an aluminium spaceship, cosmic ray comes in and hits the side of the spaceship, it's going to be a bunch of nasty nuclear reactions with the aluminium nuclei, and it's going to have like a spray of new particles. So I think it's in the ballpark of about 2 centimeters, when you'll just make things a lot worse for yourself if you have aluminium shielding, because the radiation generated is more than the radiation that is stopped by the spacecraft. So this is definitely a concern, but it's not going to stop people going to Mars or going anywhere else. So it has actually been measured. There's an experiment that went to Mars on one of the rovers, and yeah, that's a confirmed proof for what experimentally was on the other slide. See here, this is the sort of the cosmic ray soak, and these are solar proton events. So you only need to look at the cosmic rays. So what you have to do to get rid of this is to block it. You need meters of shielding to block GCR. You can block this easily. You can harden the electronics to radiation, or you can make redundant ones. And this comes back to the title of the talk, which I should maybe put an extra slide in for, but these are mass problems. The amount of shielding you can carry on your spacecraft is a function of how much mass you can throw into space. And that is a solvable problem if it's a mass problem. One further note is, going back to the Van Allen belts, there are a lot of people with this sort of idea that everything's going to be horrible as soon as you get outside them. The radiation environment inside is not that much different from the outside as you would think. The largest difference between being on the space station and being off out in space is not the radiation, the protection of the Earth's magnetic field. It's the fact that you're close to the Earth, and the Earth is like, its shadow is shielding from about half your sky, so that reduces your radiation dose by about a half, and the rest is reduces you by about a third. But these cosmic rays, which are supposedly the showstopper, they're responsible for the majority of the actual effective dose that the astronauts on the ISS receive. So this is, I'm actually going to skip this one for time. I'll go quickly. Yeah. My favourite spaceship from science fiction is the Venture Star from Avatar. It's got these big radiators on because it's just slowed down from a trip to Alpha Centauri with this fancy antimatter drive, and it's having to dump a huge amount of waste heat. This is realistic. Most science fiction doesn't bother with this. The spaceships from the Expanse, the worst thing about them is they don't have radiators. But this is a real problem for actual spacecraft. But I can show this is also a mass problem by looking at some very old Soviet spacecraft. How many of these do you recognise? Do you know what that one is? Yeah, that one? Luna 9, yeah. Do you know what that one is? Pardon? Vostok? No, not a Vostok. There's a little clue up here. It's a spy satellite. It's called a Zenit. And externally, it basically is a Vostok because this sphere, this is the return capsule, which from Vostok, Yuri Gagarin would have flown and come back in. In here, it's got a surveillance package. Now, unlike the Americans who built their hardware to live in space, the Soviets just put it inside a big pressurized capsule. And they were able to do this because at the time they were first flying these things, they flew them until the 90s, they could throw a lot more mass into space than the Americans, from 1957 to about 62, 63, I think. So they could just massively over-engineer things. So even something like thermal control is in part a mass problem. Life support is very much a mass problem. That's Biosphere 2, where they tried to do a closed loop life support and it was mixed results. So you work on a value of closure. So how much of your waste can you get back into stuff you can consume? So there's been some 90% closure experiments for certain materials. They tend to sort of exclude. You can't get 90% closure for meat, for instance. That's very tricky. And there's some very low-hanging fruit there, like water. We consume a very large mass of it, and it's fairly easy to recycle. And this is the recycling of the urine to water on the ISS, for instance. So yeah, the urine recycling in terms of mass, it has about a 24% return rate on board the ISS. So the amount of mass you have to put like spare parts for this thing, you get it back at a rate of 24% per year, which is much better than my portfolio. Gravity. Yes, gravity might be bad for you, but since I've written this slide, there's actually been some experiments on the ISS. They have a little rotating wheel for the mice. It rotates itself, they don't have to run. And they found, this is in the Japanese module, and they found that mice kept at lunar gravity don't actually suffer muscle mass loss. They only suffer from, I don't say suffer, but the types of muscle fibers swap over. from slow to fast, but then they keep their muscle mass, which is interesting. So if lunar gravity is okay, Mars gravity should be. But if it's not, if something like for pregnancy or something is bad, you can just generate artificial gravity by spinning stuff. It has to be big, because, I mean, minimum diameter is about 100 meters. Well, again, building something very, very big in space is mostly a mass problem. So, the reason that I'm sort of pointing everything out as a mass problem is that SpaceX happened. There's an image from December 2015. It's the first landing, and this was sort of the moment when I started sort of paying attention to developments in space and what they were doing, because I realised that they were actually sort of executing what they were promising, because lots of people have promised lots of things. They've only got up to 19 flights per booster, even though they lost the one that did 19 flights. It launched, it landed, but then it fell over on the barge and it just smashed to pieces. So, yeah, so they put this note in here that SpaceX are making rockets roughly the same rate that China is making rockets in the same payload class, but they're reusing them up to 20 times. So this is an incredible difference compared to what everyone else is doing. So I'm going to skip this one. This was just to sort of point out that lots of new things are happening in space. Yeah, but probably Artemis 3 is probably not 2026 anymore. But anyway. So if you plot there how much mass SpaceX has been put into space with Falcon 9, it's growing at 43% a year. So it's a doubling time, about 2 years. And there's obviously, if you see an exponential growth, you make a parallel with Moore's law. That's fairly, everyone does that. The criticism of that is obviously you just sort of extrapolating, oh, so the line goes up, great. But in my defense, if you go back to the original paper Gordon Moore wrote when he worked at Fairchild Semiconductor, it had 4 data points. So I'm doing better than he was. And I've also separated out the Starlink launches, because a lot of people say, oh, well, this is just, the demand's not there and it's just Starlink. Even without Starlink, it's 31% a year, which is very fast. Now, obviously, Falcon 9 can't do this forever. So, because there's no permanent exponentials, there's just lots of S-curves that follow on from each other. So I've tried to sort of guess where the S-curve is for Falcon 9, and annoyingly, after I made this plot over the weekend, Elon Musk gave a talk, and he's kind of ruined my calculation. Because I said, well, they're manufacturing about 10 boosters a year. They said they were going to do 20 VUSers per booster, so that means that they've got a long run rate of 200 flights a year, which seems to be sort of consistent with their current rate. But then he went and said they're going to do 40 reusers of Falcon. And why they might want to do that is because the next S-curve is Starship. Now I worked out here how many it would have to fly each year to continue the same rate at which Falcon 9 growth is seen. Around here it's not too bad, because it will have to make this many flights anyway to meet the Artemis commitments. So up to 2026, either they do it and they maintain the growth rate, or they don't do it and NASA gets very angry at them. This is completely speculative. It's up in the air because, like, literally it depends on how the next test flight goes. I personally guess they'll do 4 flights this year. I don't know how many of them will be successful. So this comes back to, so we've got a lot of the problems are just reduced to mass problems. This mass is going exponential. So the question is, when do we get to here? These big, nice colonies in space. This is from a film called The High Frontier, biography of Gerard O'Neill, which you should definitely watch. Not just because I've stolen their artwork. So when I came in when I was working in astrophysics, I thought, well, I'm not an engineer, I'm not sort of directly hands-on. I've done some sort of work on little CubeSats and balloon projects and that, but I wanted to do something, apply my knowledge of like orbits and physics and things to try and get something useful. So what I've done is I've developed a metric to measure space development. So, because it comes back to mass, I'm calling it mass value because I'm not actually talking about real masses. What I'm talking about is if somebody puts a bunch of stuff in space, like build a space station, they get some resources from the moon or whatever, you would then apply a sort of kind of a naive engineering method to say how much would it take to get all that stuff out there. And then you would be able to do direct comparisons between projects at different parts of the solar system. Because let's say you're launching stuff to low Earth orbit, you can sort of say, well, one launch company is doing better than another because they're launching a lot more kilograms than everyone else. I've just done that with SpaceX. But if you get to a situation maybe in 10, 20 years, SpaceX is launching a lot of stuff to Mars, but Blue Origin might be launching a lot more stuff to the moon. How would you compare a kilogram on the moon to a kilogram on Mars? It's not actually straightforward. So yeah, that's just a definition of the method. It's not actually that important, but you kind of have to get it right for the metric to make sense. So the idea is just have an exchange rate really of mass at various locations. So that would be the Gateway space station NASA's building around the moon. If you put 10 tons there, it would be equivalent to 40 tons in Leo and so on for the moon and Mars. Yeah, and I use kilogram equivalent because I'm not actually talking about masses here. I'm just using mass as a way to get a metric. So, a worked example of why I'm doing this. So in Mars Direct, there was am I over time?
A couple more minutes.
Okay. There's a proposal to land humans on Mars by a guy called Robert Zubrin, and he was basically annoyed that NASA was sort of proposing to launch these massive spaceships in low Earth orbit, like 3,000 tons or so, 4,000 tons, to send people to Mars on a single trip. And he proposed a way of doing it with 220-ton launchers. To manufacture, and the way he achieved this was, it was one of the first sort of widely known proposals for in-situ resource utilisation, because the key to getting the mass down was when landing the return vehicle first, manufacturing over 100 tons of methane liquid oxygen propellant on the surface before you went, and that would save huge amounts of mass. So if you work it through my equation above, it gives, for the 240 tons each mission would have to put into low Earth orbit, it would give 5,000 tons equivalent mass value. So then you can say you can work out how much your launch capability you're saving by doing this in-situ resource utilization. And so that obviously works out as a better use of launch resources on this metric compared to what NASA was proposing at the time. So just because I talked about SpaceX earlier, I should give Blue Origin a fair shake because this applies to them. They've got this lunar lander. It's going to be able to put 3,000 kilograms on the surface with a single nuclear launch when it gets done. And if you plug it through the formula, that roughly equivalent to 3 Falcon 9 launches. And Starship would require 11 flights to send anything to the moon, but it would send a lot more. So when that starts happening, I think this metric's going to be useful for working out how they're doing, because their launch systems are very different how they're getting there. And something else Blue Origin are doing, they are I added this just to mention ISIU, but fortunately the previous speaker did as well. So this is, lots of people are working on this. They want to make solar cells from the regolith. Everyone wants to make stuff from the regolith apparently. So once you add in this, the formula doesn't care where the mass came from. If you launch it from Earth, if you did ISIU, or if you did recycling, it's just mass is mass, or useful mass is mass. So this is going to help work out again a comparison between their performance. So going out to the bigger picture, an estimate of how much it would take to have a self-sustaining or set of self-sustaining colonies, I would say about 5 million tonnes a year equivalent. So if 43%, which is the current growth rate of Falcon 9 is maintained, we'd hit there only in 2045, which is incredibly soon. So it's not going to happen with Falcon 9. It is not going to happen with Starship alone, because nobody's going to permit that many launches. So the only way anything like this will happen, those big rotating spaceships, is by finding other sources of mass. So this is why the only problem that you need to solve to get all this done is the mass problem. And here's why solving it quickly is important. So there's the current, this is the growth rate on the x-axis. Y-axis is how old you are when humanity gets to that point, 5 million tonnes a year. And this is birth cohort. So I was born in 81, so I'm there. So there were two different colours. And the cutoff is the from actual aerial table. So yeah, this is when I die. So obviously, if this line shifts this way to about 25%, then I'm never going to see it. So yeah, you can find yourself on here and figure out if you'll live to see it based on whether or not you think that's going to go up or down.
And then you can make the line move right.
That's the plan.
Yeah.
This is motivation.
Yeah.
Okay, you are all going to die, so bear that in mind. So all that stuff about sort of big space companies and just like ratcheting the mass up, it basically sounds like there's nothing for ordinary people to do, for like a startup or something. But I have a suggestion. You should try to make coffee on Mars. So you're a barrister on Mars. So if in the future SpaceX makes it cost $500 a kilogram to go to Mars, so your 500-gram cup of coffee costs $250, and I don't think that even Starbucks would try that. But most of the coffee is water, and there's water on Mars. You don't take the water with you, so you put about 15 grams of ground coffee in a cup. If you mix it with local water, that's $7.50, which is more like it. But you might want a cappuccino or a latte, so if it's half milk, you back up to $132.50. Again, you do the same thing, use powdered milk, and then suddenly you've got $20 in a fairly simple set of steps. And then you can grow your own coffee. I'll let you figure out how to get the milk, because getting cows into space, I'm not sure I don't think they deal with G-forces very well. Right. So, my sort of, another action you can take is you can sign my petition. Because it's all about mass, well, almost all, mass has to come before any other engineering. I would like Starships to launch from the UK, because I think the more launch sites, more stuff gets thrown up, and hopefully somebody will listen, or at the very least it will start a conversation. Right, that's my presentation. Thank you.
Mass is all you need. Thank you very much, Peter. Speaking of mass, food's at the back. Go grab some food and we'll join back in maybe 15, 20 minutes.
The comment about making space green was about colonising, colonising space, and